Okay, so the plan for today is to finish up section 14.3 on partial derivatives and discuss section 14.4 on tangent planes and linear approximations. So a lot to finish up today. So I'm planning to get right into it, starting with the review on 14.3. So just a quick review, partial derivatives. If we have a function of two variables, two inputs, we define as partial derivatives, essentially the same way that we would define a standard derivative of a single variable, but just in relation to the variable under consideration. So the partial of f with respect to x is the limit of this difference quotient, where x is the variable that is getting the x plus h in the first term in the numerator. So limit h goes to 0 of f of x plus h comma y minus f of xy over h. And we saw that as a result of this definition, we see that partial derivatives pretty much work like single variable derivatives, where we consider the variable of differentiation to be a variable, and any other variables, like say the y, for instance, here, we note that it is not changing. It's just y here and y there. So we just treat it as a constant. We also discussed some notation. I'll typically use the subscript notation just because it's easier to write out by hand, but also a pretty common notation is this notation here, partial of f with respect to x, where these little kind of d looking things are really curly d's. They're not the same as regular d's for derivatives. Okay. Last time we discussed the first couple bits of example 1, computing df dx and df dy in general and evaluating those at the point 1 comma 2. And we saw that for the function f of xy equals 2x squared minus 3xy plus 4y cubed, we ended up with these partials. df dx was 4x minus 3y. And again, going term by term. Yeah, somebody asked in chat, are we going to finish Monday's notes? And that's basically where we're picking up off of here. So this should be picking up more or less off of Monday's notes. I did change a couple of things slightly just for time considerations, but this should look familiar for Monday. So df dx, this first term does have x's in it. So it's we're going to differentiate it. D by dx of 2x squared gives me just 4x. My middle term also has an x in it. It also has a y though. Remember, I'm treating y as a constant here for df dx. So this minus 3y is a constant multiplying the variable x. Well, constant times x, the derivative of that is just constant. So I'm left with just my minus 3y, my constant, so to speak, from this middle term. And then the third term here, 4y cubed, doesn't have any x's in it. From the perspective of differentiating with respect to x, this is just a constant, and the derivative of a constant is 0. So that's our x partial, and then our y partial was very similar. For part B down here, we worked through this example, and it took a little bit more calculation, a little bit more work, but we had to use the quotient rule for these, but we were able to get the partial derivative with respect to x and with respect to y for this function as well. Okay, let's look at function C here. This is also a little bit of a review of some Calc 1 concepts, derivatives, and so on. And just a reminder of what we talked about last time. So again, I want my my partials, partial with respect to x and with respect to y. So let's start with df dx. Taking y to be constant, this 1 over y multiplying the exponential function is just a constant. So it just comes out. So the derivative of 1 over y times the exponential is just 1 over y times the derivative of the exponential. That constant just comes out. D by dx of this exponential, well, this exponential function does have x's in it, so I'm going to use the chain rule here. The derivative of e to the stuff is e to the stuff times the derivative of the stuff inside. And of course, when we say the derivative of the stuff inside, we're talking about, again, the partial with respect to x of the argument inside of the exponential function. I'm writing it this way as the exponential function with an argument instead of an e to the power, because putting all of this stuff up in the power would be very hard to read. But again, the derivative d by dx of the exponential function with this stuff in the power is e to the stuff times the derivative of the stuff, d by dx of the stuff inside the exponential function. This minus 1 over 2y squared, again, we treat as a constant. It just comes out of that derivative, times d by dx of a minus x squared, that is 2 a minus x to the first. And then again, another application of the chain rule pops out a -1, a factor of -1 from this minus on the x here. And that just makes this a +1. That 1 over 2y squared just gets a +1 now. And I'll leave it like this. I mean, we could simplify it a little bit, but I'll leave it here. What about the fdy? Well, here I note that I have a product of two functions of y. The exponential has some y's in it, and also the 1 over y is obviously a function of y. Need to use the product rule here. So if I differentiate the first, differentiating y to the -1 gives me a minus y to the -2 multiplied by the second, the exponential function with that same argument, plus the first times d dy of this exponential function, now taking x to be constant. So the derivative of e to the stuff with y in it is e to the stuff times the derivative with respect to y of the stuff inside the function. Well, from the perspective of y, this negative a minus x all squared that's all constant. That can just come out of the derivative with respect to y, and also the 2 on the bottom can come out. And all I'm left with is differentiating 1 over y squared, or y to the -2, which differentiates to -2 y to the -3 power. And again, I could clean this up quite a bit. I could pull out the exponential, combine some of these factors of y. I'm just going to leave it here, though. That's just a bunch of algebra to make it look a little nicer. If you're not good with your chain rule from Calc 1, do take a little bit of time and drill that, practice that. That is a very important thing to be good at for really the rest of the course here. Okay, so moving on to example 2, what if we have a function of more than 2 variables? What happens there? Well, the partials work exactly the same way. So for instance, if we look at f of x, y, z, and t being ct squared minus x squared plus y squared plus z squared, this is an important invariant in special relativity. So we can take the partial of f with respect to any of its 4 variables. So for instance, the f dx is going to be, well, ct squared from the perspective of x is just a constant. It differentiates off to 0. I have a minus x squared term that differentiates to a minus 2x. I also have a minus y squared term and a minus z squared term. Again, from the perspective of x, they're both constants. They differentiate to 0. We can also see there's a lot of symmetry here. Y and z behave just the same way. So obviously, the partial f with respect to y is going to be -2y, and with respect to z, -2z. The partial with respect to t is a little bit different. We see this whole x squared plus y squared plus z squared bit here at the end is all constant with respect to t, so that differentiates to 0. But ct squared, when I take its derivative with respect to t, I get 2ct. So it's positive, and it has this factor of c, the speed of light, in there as well. Okay, let's look at part B of example 2. Here we have, we're considering a vector with components x1 through xn, and the length of that vector is a function of those components, x1 through xn. It's the square root of the sum of the squares. So how does the length of a vector change with one of its components? What is the partial with respect to, let's say, component I? The partial derivative of L with respect to x sub I. We see that, x1 through xn, these are all individually kind of treated the same. There's a lot of symmetry here. If I swap any two of them, I get the same thing back. So the symmetry means I just have to look at how one component's partial looks, and that gives me the answer for all of them. Well, I have function of xi to the 1/2, or square root of some function of xi. So that gives me 1/2 root of that stuff. I have a factor of 2 in front, but then my chain rule says I need to take the partial with respect to xi of x1 squared plus x2 squared and so on through xn squared. All of those x1 and xn and so on that aren't the xi term, they all differentiate to 0 because they're constant from the perspective of xi, and it's just the xi term, xi squared, that differentiates the 2 times xi. The 2 that would come down cancels the 2 from the 1/2 root from that derivative. And this is our partial, it's xi over square root of x1 squared through xn squared. Or it's just xi over the length. And then let's look at part C here. I'm going to do one part. I'll leave the other two as exercises. So here I have a function g of ABC equals the familiar quadratic formula. But here we're thinking of the quadratic formula as being a function of the coefficients, a, b, and c, of a quadratic. As I change the coefficients of a quadratic, my roots change. So how do the roots of a quadratic change with respect to each of the coefficients? I'm going to take a look at maybe g sub b here, and I'll leave g sub a and g sub c as exercises. These aren't the prettiest formulas, so don't expect that you're going to get a whole bunch of cancellation or that you're going to get a super simple looking answer. These aren't super pretty formulas. So the first thing I'm going to do is I'm going to take a look at g here, and I see that, well, I have a bunch of stuff in the numerator that has b's in it, but the denominator doesn't have any b's. So the partial of g with respect to b is going to be 1/2a. That constant comes out times the partial with respect to b of this numerator. The first term of the numerator, negative b, the partial of that with respect to b is just -1, then plus or minus. And now I have square root of a function of b, so I get 1/2 root of that stuff inside, b squared minus 4ac. And then again, my chain rule says I need to take the partial with respect to b of the inside, b squared minus 4ac. Well, 4ac is a constant from the perspective of b. It differentiates off. The derivative of b squared is 2b. And again, that 2 in the numerator that comes down from the b squared cancels the 2 in the denominator from the 1/2 root stuff. And that's what we end up with. Okay. Any questions so far? Now, there's something I mentioned before, and I think I even said last time that I really didn't fully appreciate this until maybe grad school. So I want to point it out here because I think this really highlights something important about partial derivatives. And I suppose this is maybe in a sense a notational consideration, but it's an important idea. What if I thought of having a function like this, a function of three variables, say x, y, and y prime being dy dx. I'm thinking of f having three arguments, three different inputs here, x, y, and y prime. And let's just say that my function is square root of x squared plus y prime squared. What's my partial with respect to x of f, partial with respect to y of f, and what is my partial with respect to y prime of f? This idea actually comes up in an area called calculus of variations. You might see it a little bit in physics. It's used a bit in economics. It's used a good bit in physics at some of the higher level physics courses. And obviously it's used in math as well. And this kind of a thing comes up. And this confused the heck out of me until I actually worked out what was going on. Remember up here, and I mentioned this last time also, that we're kind of abusing the notation here a little bit. When I say something like f sub x of xy, this x comma y for the inputs is kind of an arbitrary input, but this subscript x is actually just indicating I'm taking the partial derivative with respect to the first variable in the list. I'm actually using x in kind of two different ways here. So when I say the partial of f with respect to x, what I mean is with respect to this first variable. I see what I have here is square root of the first variable squared plus some other constant stuff. So let me get myself a little more room here. So df dx is going to be 1 over 2 root x squared plus y prime squared times 2x. Right. If I think of what is this kind of, it's if I imagine a vector that has length or that has components x, y, and y prime, this is just its length. This is really just the same question that we answered up here. It just looks a little different because I have some y's and y primes and things I'm not so used to seeing as arguments. What's the FDY? Well, again, I'm just saying my second input, that's what I'm differentiating with respect to. So I have the square root of some constant plus second input squared plus some other constant. And if I ask something like, what's the partial with respect to y prime of f sub y prime, this is going to look very confusing, right? But really all we're doing is we're indicating we're interested in the third argument. And I see my function just says it's the square root of some constant, and from the perspective of the third argument, plus the third argument squared. Or in other words, fy prime is just y prime over the square root. So I'm just pointing this out to highlight the fact that we're using this this subscript to indicate which argument we're taking the derivative with respect to. Right? Instead of having a y prime here, I could have put a smiley face here or something and called it DFD smiley face. And I would have gotten the same thing just with smiley faces instead of y primes on the right-hand side. Any questions so far? Okay, so one thing that we notice is that our first partials end up typically being functions or end up being functions. And therefore, just like single variable calculus, we can take their partials. So for instance, I could take the partial with f with respect to x. That's a function of x and y. And I could take the partial of that with respect to x, giving me, for instance, fxx, one of the second partials of f. Sometimes we would write d squared over dx squared of f, or partial with respect to x of partial with respect to x of f. So let's take a look at the function that we took first partials for earlier, well, actually last class, and then reviewed earlier. And let's find its two second partials, fxx and fyy. And for convenience, I've just noted what we figured out the first partials were right here. So what's fxx? Well, this is the partial with respect to x of fx. Again, that's a two variable function. It has some x's and some y's. Considering the y's to be constant and the x's to be variables. So 4x differentiates to 4, and minus 3y, well, from the perspective of x, that's just a constant that differentiates to 0. So fxx in this case is just the constant function 4. And what is fyy? Again, that's the partial with respect to y of fy. We're taking the partial derivative of this function, negative 3x plus 12y squared. And again, since we're differentiating with respect to y, that negative 3x is a constant. It differentiates to 0. And the 12y squared, taking the partial with respect to y, gives me 24y. So for that original function, this polynomial, these are our second order partials, fxx and fyy. And we might ask then, well, if fx is just a function of two variables, we could take its x partial, but couldn't we take fx's y partial, or maybe fy's x partial? Seems plausible that we could do that. Those would also be second order partials, but they're what we would call mixed partials. So let's compute those for this function. Let's first compute fxy, which is the partial with respect to y of fx. Or that is the partial with respect to y of the function 4x minus 3y. And again, from the perspective of y, 4x is a constant, so its derivative 0, and negative 3y differentiates to just negative 3. What about fyx? Or in other words, taking the x partial of fy, or taking the partial with respect to x of fy as negative 3x plus 12y squared. Here, negative 3x is a function of x that differentiates to negative 3, and the 12y squared is a constant from the perspective of x, so it differentiates to 0. We actually notice the mixed partials are equal to one another. Is this a coincidence? Does this tend to happen? Well, we have a theorem called Clairaut's theorem, and it says that if the mixed partials exist and are continuous, then they are equal. not just if they exist, they're equal, but they have to exist and be continuous on some disk containing the point we're interested in. If that's true, then they're equal at that point. But kind of for practical purposes, most functions are going to come across when you're, say, taking a physics class or something like that, or even in this class for the most part. The mixed partials are typically going to be equal. You know, we're typically working with polynomials or exponentials or trig functions that are very nicely behaved. Okay, so let's look at these two examples. For example, for A and B, we'll compute all first and second order partial derivatives for these functions. So we'll have two first order derivative, fx and fy, and we'll have three second order, fxx, fyy, and fxy, which will be just the same as fyx. So df dx, I see that nicely enough, this is a product of two functions, where one of the functions only has x's and no y's, and the other function only has y's and no x's. So from the perspective of x, this whole sine y squared is just a constant. It just kind of comes along for the ride. We differentiate e to the 2x as 2 e to the 2x sine y squared. We can figure out the second partial, fxx, as the x derivative of fx. Again, this sine y squared is just a constant, as is the 2 in front. That all just comes out, and I just differentiate e to the 2x again to get 2 times 2 is 4, e to the 2x sine y squared. And I could figure out the mixed partial, fxy. I'll do the y derivative, the y partial of fx. That's going to give me 2e to the 2x. From the perspective of the y partial, this 2e to the 2x is constant now. And then sine of y squared, well, sine of a function of y differentiates the cos of y squared times the derivative of the inside is 2y. Or this is going to be 4y e to the 2x cosine y squared. Okay, now what about fy? Well, from the perspective of the partial with respect to y, e to the 2x is constant. So it just comes out, and then I take the partial with respect to y of sine of y squared. That's cos of y squared times 2y. And I'll leave that like this so that my kind of y's are together and my x's are together. You know, often we would pop that 2y all in front of the exponential. It's just kind of the way we're used to seeing it, but I'll leave it in this form since we want to take further partials. So what's fyy then? I wrote that a little close. Well, that's the y partial of fy. E to the 2x comes out. So does the 2. I'll bring this 2 just out in front here. And now I need to take the partial with respect to y of cos of y squared times y. Well, I better use the product rule here. That's the first times the derivative of the second. Cos of y squared times 1 plus the second times the derivative of the first. Derivative with respect to y of cos of y squared is negative sine of y squared. Negative sine of y squared, and then times the derivative of the stuff inside, which is 2y. That just leaves me with a 2y squared out there. So that's fyy, a little messier than fxx. but it is what it is. Okay, so any questions? Any questions so far? All right, so on to B then. F of x and t is sine of ax minus bt. So df dx, I see I have sine of a function of x, that's going to differentiate to cos ax minus bt. And then the chain rule is going to pop out a factor of a. fxx, well, the factor of a just comes out. I differentiate cosine and minus sine. I get another factor of a coming out. Or this just turns out to be minus a squared f. What is ft? I'll probably say fy at least once here because I'm used to the second variable being y, but what is the dt? Partial f with respect to t. Well, again, that's sine of a function of t I'm differentiating, so it's cos ax minus bt times the partial with respect to t of ax minus bt, and that's just minus b. What is ftt? The t partial of ft. My cosine differentiates to negative sine. I get another negative b that comes out. So I have a positive b squared from the b's, but then a negative because the cosine differentiates to a negative sine. So negative b squared sine ax minus bt. Or this is negative b squared times f. And then what's fxt? I could take the t derivative of fx or the x derivative of ft. Either way is going to give me the same answer. I'll do the t derivative of fx. So differentiating cos of ax minus bt with respect to t, that's going to give me a minus b coming out. But cosine differentiates to negative sine, so that cancels that sine. Sine of ax minus bt. Or it's just ab times f. Any questions so far? Okay, so we kind of see the nuts and bolts of partial derivatives aren't all that bad. It's kind of just like doing Calc 1 a few different times. What's the geometric interpretation of partial derivatives? Whenever we, in Calc 1, introduce the idea of a derivative, we have kind of the algebraic side of things, with limits and working with the algebra and so on, but we also have the graphical side of things. So let's consider a surface in R3, z equals f of xy, that contains the point a comma b comma f of ab. So the input is ab. If I can select it here, the input is a comma b, and the height, the z value, is f of ab, the output. If we consider the function f of x comma b, in other words, holding the y value, the y input constant, and varying the x input, well, that variation only happens along a single direction, along the x direction. F of xb, we could just call g of x. It's just a single variable function of x. In other words, it represents the curve where the vertical plane y equals b intersects the surface. We drew these, kind of a depiction of this last time, where we had a surface. I'll draw it somewhat quickly here. It won't be super pretty, but you get the idea. So we have a surface here that's above, say, a domain, and this domain is where the point A comma B lives. And this point up here, I missed my mark there a little bit. I wanted it to be at that crosshairs, but this point up here is the point A comma B comma f of AB, which is the associated z value. If I hold y constant, and if I move along this direction here, if I move back and forth along this green line, my input is only changing along one dimension. I can really kind of imagine that, we're taking this to be y and this to be x, the way that I'm describing it. I got my x's and y's backwards when I drew it, but the point still holds. We can imagine this plane here where it intersects this surface. That's really just a single variable function. It has one input where I'm at along that green line in the xy plane, and one output, the height. So it feels very much like Calc 1. And similarly, we could go the other direction. F of A comma Y is just some other function just of Y, where we have the intersection going in the other direction. And again, each of these curves can be thought of as a function with one input and one output, just like a Calc 1 type function, a single variable function. And each curve has a tangent line that lies in its associated plane, right? Pretty clearly, the tangent line to this red curve lies in that plane. If we rewrite these functions little g and little h, remember they represent space curves. They represent some, tracing in three-dimensional space, really. We're kind of envisioning it as a two-dimensional space because it's only operating in this plane, but it is in three-dimensional space. We could envision these or rewrite them as vector functions. We have the vector function g of x equals, well, g of x is associated with the input x comma b and the output f of xb. The input, the xy coordinate x comma b, and the z coordinate f of xb. And similarly for h, where our input is the point a comma y and output f of ay. I can find g prime of x and h prime of y. G prime of x, well, the first component differentiates to 1, the second to 0, because the second component is not changing as x changes. And then f of x comma b, well, that differentiates, well, here when we say g prime of x, we're talking about differentiating with respect to x. That differentiates to the partial of f with respect to x of xb. Similarly with h of y, differentiating this function, this vector function with respect to y, the first two components differentiate to 0 and 1, and the third differentiates to the y partial, because again here y is the variable of interest, differentiates to the y partial fy of ay. So at the point of interest, we have two tangent lines, say this red one that's going in this plane that's parallel to the xz plane, and this black tangent line that's going along in a plane that's parallel to the yz plane. We have two different lines in space, these two different tangent lines. They go through the point A, B, f of AB, and they have direction vectors given by these directions, 1, 0 fx or 0, 1 fy. So we see that these are the, let me try to line these up just a little bit better. Oh, I didn't want to add more space there. I want to add more space down here. Yeah, line these up a little better just so that they're a little easier for you to see what's going on. So these two lines have first component, well, let's say they have vector a, b, f of a, b plus t times 1, 0, fx, right? The starting point plus t times the direction vector. That should look familiar. So that's the direction vector. This is the starting point when x equals a, or it's just this point up here. And then similarly for the h's, again, we start at a, b, f of a, b. That's the point of tangency. And then we have direction vector 0, 1, fy that's being multiplied by s, a different parameter from the first one. So how can we envision this? Well, we can envision this as saying if we move a distance t in the x direction in the input space down here, what effect does that have on the output, on the height of the function? Well, we don't know exactly, but we can approximate it by the tangent line. So if we move a distance t in the x direction in the input space, that causes an approximate increase of t times fx of ab in the z direction, right? Moving t units in x changes my output, my height, my z value by approximately t fx. And similarly for moving s units in the y direction, causes approximately an output change of s fy. Or these partial derivatives are basically saying, when I have a change in the input space, how is that magnified to a change in the output? When I have a change in the xy axis for the input, how does that change z approximately? Okay. I think for this one, I'm going to do maybe example 5a and leave the others as just exercises. Actually, I'll do 5a and b. They're pretty quick. But I'll leave example 6 as an exercise. It's a pretty straightforward exercise. So leave that as an exercise. But example 5a and b, we have a function here, u of xt equals sine of ax minus bt. And we've seen differential equations before. We should have anyway. Both in Calc 1, you probably saw some differential equations where you were just told, show that this function satisfies this differential equation. Maybe something like show that y equals e to the x satisfies like y prime equals y or something like that. And then in Calc 2, you should have seen a little bit about solving differential equations. So if you were just given, say, y prime equals y, how would you solve that? Those differential equations were all related to regular derivatives. But we could also have equations that relate functions to their partial derivatives, that relate functions of several variables to their partial derivatives. These are actually quite a bit more complicated than regular differential equations. We're not going to be looking at solving these from first principles, but we will attempt to show that certain functions satisfy certain PDEs. Now remember, this sine of ax minus bt, that is the function that we had up here. So I'm actually just going to kind of lasso select this whole thing. And I'm going to copy it down here. hopefully it will copy okay. All right. So we already did most of the work for this. Oops, I got it a bit wonky, but I think we can just, there we go, just move that out of the way. So our claim is that this function satisfies both the so-called transport equation, a times du dt plus b du dx equals 0, as well as the wave equation, a squared times the second partial of u with respect to t equals b squared times the second partial of u with respect to x. Or often the wave equation would we divide through by the a squared and just make that constant on the right side. So is it true that AUT plus BUX equals 0? Well, so B, here I have F's instead of U's, but BF equals AB cos of AX minus BT. Is that equal to negative BFX? Is that equal to negative AFT? Well, AFT is going to be negative AB cos of stuff, so that is indeed equal to negative A partial F with respect to T. So we see just looking at these two, that is true. Or another way I could look at it is just take df dx, partial F with respect to X, multiply it by B, that gives me AB cos of stuff. Take partial F with respect to T and multiply it by A, that gives me negative AB cos of stuff. The two add together to get 0. Is it true that the wave equation, A squared times the second partial of u with respect to T equals B squared times the second partial of u with respect to X? Well, the second partials with respect to X and T, I see are, again, only off by a constant multiple. The second partial with respect to X, if I multiply it by B squared, I get negative A squared B squared F times, where F is my original function here. And if I multiply the second partial with respect to T by A squared, I get exactly the same thing. So these are indeed equal. So most of the demonstration was really just in computing all of these partial derivatives and then just showing that these that the algebra works out. Again, I'll leave it as an exercise for exercise 6 here to show that this function, e to the minus alpha squared k squared t times sine of kx, satisfies the heat equation, partial of u with respect to t equals alpha squared times the second partial of u with respect to x. Any questions on partial derivatives? Okay, let's jump into 14.4 then. This will start the last section for this week's work. We still have several more sections in chapter 14, but for this week, this is all we're going to look at. We might finish this section up today, or chances are pretty good that we won't quite get through it today, and then I'll probably post a bit of a supplement tomorrow just to wrap up the rest of this. And that will actually be up early. I know the supplement last night came out much later than I was expecting. I had something in the morning that ended up taking several hours longer than I had expected. So I wasn't able to get around to putting that together, getting everything recorded and posted and everything until later. But this should be a shorter supplement, and fingers crossed, nothing will kind of blow up tomorrow. Okay, so tangent planes and linear approximations. We recognize these ideas from Calc 1. The idea of a tangent line, the idea of a linear approximation, where we're basically saying that a tangent line close to its point of tangency is a good approximation to the function, and the idea of a differential, which is closely related to a linear approximation. How do these ideas generalize to functions with several variables? That's what we're looking at now. Kind of two of my favorite quotes related to these ideas of linear approximations, and one of them I actually don't know where the origin is or who said it, but it's kind of a funny quote that I think is fairly commonly known in the math world, is the statement that goes something like dividing the world into linear versus nonlinear phenomena is like dividing all objects into bananas and not bananas. So in other words, essentially any problem that we look at and that we're interested in is going to be nonlinear. So why are we making such a big deal about all of this linear stuff? We're talking so much about lines and planes, and but pretty much anything we want to study is not a line or a plane. Those tend to be very contrived examples. Why do we care about this? Well, my favorite professor, Bill Layton from University of Pittsburgh, now retired, he would love to say the world is locally linear, or linear algebra is where the rubber meets the road. So what does this mean that the world is locally linear? It means that, well, if our functions are smooth, even if they're non-linear, if they don't have, points or jumps or cusps, which most of the things that we're interested in studying are, smooth in nature, that means that if we look close by a point of tangency, the tangent line or the tangent plane is a reasonably good approximation to that curve or that surface, even though it's nonlinear, when we're near that point of tangency. This idea of local linearity is pretty similar to the idea of differentiability. I suppose depending on, who you argue with, you might say it's essentially the same thing. You might say that there's a slight nuance that's maybe locally linear is a little bit different, but it's essentially the same thing. Okay, so I would like to find a tangent plane. In other words, if I have a surface, let me draw my little surface here again. And a point of interest on that surface, I would like to find a plane. Whoops. I would like to find a plane that's tangent to that surface. In other words, I would like to find a flat sheet of paper that if I lower it down onto that surface, it's going to touch it at just that one point of interest. Now, the plane isn't the same thing as the surface, but I can understand the plane much more easily than a complicated surface. If I vary my input a little bit, instead of asking how does that vary the output along the surface, which is quite a complicated question to answer, I could ask how does that vary the output along the plane, the tangent plane, and that's a much simpler answer to give. And so long as the input that I'm interested in is close to the point of tangency, what does that mean? Well, maybe that's a more difficult question to answer, but so long as it's close enough to the point of tangency, I mean, my answer is not going to be exact, the plane versus the surface, but it should be pretty close. It should be a good approximation. And that's the whole thrust of this section, tangent planes, linear approximations. Okay, so recall from the discussion on the geometric interpretation of partial derivatives, we had these vector functions g and h, and we said that g prime and h prime were tangent vectors to space curves that were in that surface. So we want to find an equation for the tangent plane. This is going to be the plane that contains these two tangent lines, g prime and h prime. Okay, so thinking back a couple of chapters, if I have two vectors that lie in a plane and I want to find the formula for the plane, well, to find the formula for the plane, I need a normal to the plane. And to find a normal, the go-to method is to take a cross product. So let me take my normal to be G prime cross H prime. And G prime is 1, 0 fx, which I'll just abbreviate this way, but this is fx at AB in this case, because we're at the point of tangency here. And H prime is going to be 0, 1 fy at AB, 0, 1 fy at the point AB. What is my first component? Well, going down the main diagonal, I times 0 times fy gives me 0. And then minus I times fx times 1 gives me minus fx at AB for my first component. The j bit, going kind of down and to the right, j times fx times 0 gives me 0, minus j times 1 times fy, minus fy at AB. And then k going down and to the right gives me k times 1 is 1, minus k times 0 is 0. So that is my normal. And then what's the formula for my plane? Well, it's the first component of the normal times x minus a plus second component of normal times y minus b plus third component times z minus z naught. So I have negative fx of ab times x minus a plus a negative fy of ab y minus b plus 1, I'll put the 1 in there, times z minus, well, let's just call it z naught for now. This is for the point A, comma B, comma z naught. And that's equal to 0. Or this tells me that z minus z naught equals fx of ab times x minus a plus fy at ab y minus b. That's one way to view this. I could also note that z naught is actually f of ab, because we're on this surface representing the graph of f, right? So I could rearrange things and say that z is f of ab plus fx of ab times x minus a plus fy of ab y minus b. And importantly, this is my tangent plane. So I'm not saying that this is true for the z value of the surface as I'm moving along the surface. I'm saying this is what's true of the z value as I'm moving along the plane that is tangent to the surface. So important distinction. Why do we want to work with tangent planes instead of surfaces? Because these functions are much easier to deal with. I see that as I wiggle x or y, my inputs, that wiggle is magnified to the output approximately through the partial derivative at that point, AB. Okay, so let's look at an example here. Find the tangent plane to the graph of f of xy equals 3x squared plus 2y squared minus 11 at xy equals 2, 1. I'm going to give this a shot at drawing this. I'm not going to be super careful with coordinates and things on the axes, but I know that when x and y are 0, z is minus 11. So down here on the z-axis. I know that if, say, y is 0, as x increases positive or negative, eventually we cross the x-axis. Say maybe something like here, and maybe something like there. I know that when, so this is x, y, and z. I know that when x is 0, as I move y away from 0, it kind of, my quadratic comes up like this, intersects the y-axis at some point in the positive or negative direction. So for instance, a level curve at 0, at z equals 0, would be this ellipse here, a level that goes through these 4 points. A level curve at, say, z equals 1 might look like this. That goes through these 4 points. So it looks like a kind of cup opening upwards. It looks like a paraboloid, or more or less like a parabola, but just rotated around. It's not exactly that because it's kind of elliptical, but it's more or less like if you took a parabola and rotated it about the z-axis. At the point xy equals 2, 1, that's, say, maybe in my xy plane, maybe that's like a point here. So 2, 1, f of 2, 1 is this point in 3-dimensional space. I'm looking for a normal vector and a tangent plane at that point. So that's my goal here. I know it's probably very difficult to, I mean, I have an idea of what I'm drawing, so I can kind of see it, but I know it's probably difficult to track on your end. You can look in the book and they give better diagrams that are computer generated, but hopefully this at least gives you an idea of what we're looking for. Okay, so what do I need for my tangent plane? Well, I need the partials, and I need to evaluate the partials at AB. So let's start there. df dx is going to be 6x, and df dy is going to be 4y. Something very common that folks do both in Calc 1 and in Calc 3 is they get here and then they plug, 6x in here and 4y in there. Remember, the whole idea is to get a tangent plane, a linear function. If I have 6x times x minus a, that's a quadratic. Or really, the partial of f with respect to x could be really any function. It could be an exponential function or a sine or something. The goal is to figure out the values of these partials at the point of tangency. So fx of 2, 1, x equals 2, y equals 1 is 6 times 2, or 12. And fy of 2, 1, when x is 2, y is 1, is just 4. I also need f of AB. What is that? That's 3 times 2 squared is 4, plus 2 times 1 squared is 1, minus 11. 12, 14 minus 11 is 3. So my tangent plane is z equals f of AB, or 3, plus df dx at the point 2, 1 is 12 times x minus 2, plus df dy at the point of tangency, 4 times y minus 1. So I could write this like that. I could write it as z minus 3 equals the other stuff too, kind of whichever way you prefer to write it. But I like this way because it kind of shows me directly how changing the inputs, X and Y, affects the output, very importantly, the output on the tangent plane, not on the surface itself, but on the approximation to the surface. Okay, let's find a tangent plane to the graph of f of xy equals natural log of x minus 2y when xy equals 3, 1. So similarly, I'm not going to try to draw this one. That would be a pretty nasty function to try to draw. What's f of 3, 1? That's log of 3 minus 2. Log of 1 is 0. What's the FDX of x, y? Well, I'm taking the derivative with respect to x. I have log of stuff with x in it, so I get 1 over stuff, 1 over x minus 2y times the partial with respect to x of x minus 2y, but that's just 1. The 2y is constant, differentiates off. And fx of 3, 1, when x equals 3, y equals 1 is 1 over 1, or just 1. Fy of xy, again, we have log of a function of y, so we get 1 over x minus 2y, and then the chain rule now pops out a -2 from taking the partial with respect to y of x minus 2y. And fy of 3, 1 is -2 over 1 is -2. And here we have z equals, and I'll write all of this extra stuff in just so we see where everything ends up. 0 plus 1 times x minus 3 plus -2 times y minus 1. Or written a little more simply, z equals x minus 3 minus 2 times y minus 1. And here, just kind of for my conceptual clarity, I would probably actually put parentheses around the x minus 3. It's certainly not wrong if you don't do that. It's not necessary. But this just reminds me that I'm looking for kind of the perspective I'm taking here is deviations of x from 3 and deviations of y from 1 cause deviations from that point of tangency. So this would be my tangent plane to the graph of this function at the input 3, 1, or at the three-dimensional point 3, 1, 0. Any questions? Okay, so moving on to linear and a little bit on quadratic approximations. This is all going to build on the same mathematics we just did. This idea of the tangent plane. We're just kind of shifting perspective a little bit in one case or the other. So for linear approximations, we can define L of xy equals f of ab plus fx at ab times x minus a plus fy at ab times y minus b. L of xy is just the function that results in a surface that's this tangent plane, right? So z equals L of x, y. It's the graph of that is the surface that's the tangent plane. The tangent plane to f of xy at the point AB. And remember, the idea is that I can approximate my complicated, probably nonlinear function, my nonlinear surface, f of xy, by this nice linear function, L of xy. I can approximate this complicated surface by a nice simple plane, a flat plane, so long as I don't deviate too far from the point of tangency. Then if I deviate too far, my approximation is probably going to get quite bad. But if I stay close to the point of tangency, my approximation should be reasonably good. Okay. The idea is, again, that I can approximate f by L, and therefore I can approximate the value of f of xy by L of xy for inputs xy near AB. Obviously, the two are equal at AB, but if I stay near AB, I can get an approximation. Let's look at this example. So electrical power can be computed as P, the power, is a function of E and R, the voltage and the resistance, by E squared over R. So P of ER equals E squared over R, just Ohm's law. Power is volts times amps, and then just use Ohm's law. So again, E is voltage, R is resistance. So first, let's compute the linear approximation, L of ER. And we're going to do this kind of in general. So my linear approximation is going to be what? It's going to be P of E naught, R naught. Here I'm using the points, the naught points to be like A and B. So like A equals E naught, B equals R naught, and then X equals E, Y equals R is kind of the association with these variables up here. So E and R I'm taking to be the variable names, and E naught and R naught to be the specific points, the specific point, I guess, E naught comma R naught, where I'm taking the point of tangency to be. So P of E naught R naught plus dP dE of E naught R naught times E minus E naught plus dP dR of E naught R naught times R minus R naught. This is just what we have up here. You can just think of it in terms of like first variable and second variable or something. Or you can think of it as just kind of this mapping from up above. Okay, so P of E naught R naught, I guess, is E naught squared over R naught. Okay, what is the partial of P with respect to E? P sub E is 2E over R. And here it is very important, again, that I evaluate this at that point, E naught, R naught. I don't want to leave this as 2E over R, because then again, I'm going to get like a 2E squared. I'm going to have 2E squared over R. That is certainly not linear in E or R. I evaluate at the point E naught, R naught. So very important to be careful with notation here. Times E minus E naught. And then plus, well, the PDR, well, P is E squared R to the minus 1. The PDR is minus E squared R to the minus 2. So this isn't going to be a plus, it's going to be a minus. So minus E naught squared R naught squared, E naught squared over R naught squared times R minus R naught. That is L of E comma R, my linear approximation. E and R are the variables that can change, that I can put in a value other than E naught and R naught, other than say 120 and 2000. Okay, so part B, we're actually going to see something kind of interesting come out here. So we're going to jump to part B. Approximate the maximum percent error when calculating power when the maximum percent errors in measuring voltage and resistance are 3% and 4%. So I know that anytime I make a measurement, there's going to be an error associated with it. I have input errors into the function. How do those errors cascade through the function to the output, to the power? If I make errors when measuring the voltage and resistance, how does that translate through to an error in my estimate for the power? I want percent error. So what's percent error in, say, power? It's something like P minus P naught over P naught, right? That's percent error, relative error. Well, I know that P of E comma R is approximately L of E comma R, right? Or it's a P of E comma R is approximately P of E naught R naught plus all of this other stuff. All of this stuff. Or in other words, P of E comma R minus P of E naught comma R naught is approximately equal to 2 E naught over R naught times E minus E naught minus E naught squared over R naught squared, R minus R naught. This is what my linear approximation gets me. Let me work with this right-hand side a little bit. Right now, E minus E naught and R minus R naught are kind of actual errors, but I want relative errors. I would like something like E minus E naught over E naught, or R minus R naught over R naught. Let me massage this a little bit. I want E minus E naught over E naught. But if I put one in the bottom, I better put one in the top too. So that gives me 2 E naught squared over R naught. And then minus, again, here I want R minus R naught over R naught. But here I kind of stole one off of the bottom. So I have an E naught squared over R naught, not squared on the bottom. Or this is just, well, it's E naught squared over R naught, that factors out, times twice the relative error in E, minus the relative error in R. So this works out very nicely for this particular function, because I noticed that E naught squared over R naught, that actually is exactly what P of E naught R naught is. Meaning I can divide both sides by that. So that relative error in P is approximately, I've gotten rid of this factor, that's what I divided through by, is approximately twice the relative error in E. Oops. Minus the relative error in R. So this, I'm going to put a red box around this because this is, we did a lot of work to get that, and that is really the crux of the problem. The relative error in P looks like twice the relative error in E minus the relative error in R. Or what's the max relative error in P? Well, something that I don't want to say, my relative error in E is plus 3% and my relative error in R is necessarily plus 4% also, so that they kind of cancel out. I could overestimate E and underestimate R so that they add together, or underestimate E and overestimate R. So I really have to kind of look at absolute errors here. The maximum relative error in P is going to look like twice the max relative error in E, which is 3%. And then plus, again, because I want to take into account the fact that these errors are kind of independent of one another. It's not like if I overestimate E, I've necessarily overestimated R. I don't know whether I overestimated or underestimated R. The worst case scenario would be to overestimate E and underestimate R, or vice versa, to get even more error. So I'm going to say plus 1 times my relative error in R, 4%, or that is 10%. So with these bounds on the relative errors for E and R, for those measurements, my bound for my relative error for the power is going to be about 10%. Much easier to do this using linear approximations than to try to do this using the original function. And then C, how would we construct a quadratic or a second order approximation of P? I'll just kind of give the answer quickly here. We're going to see more on this later on in the course, but we could say that P of E comma R is approximately quadratic approximation of E comma R, which would be linear approximation plus the quadratic bits plus, and I realized when I was writing my notes that this came up as P subscript EE, so sorry about that, but P sub EE of E naught R naught, the second partial with respect to E, times E minus E naught squared, plus P sub ER, E naught R naught, E minus E naught times R minus R naught, plus P sub RR, E naught R naught times R minus R naught squared. These would be the quadratic terms that would be added on to the linear terms. And we see that we can actually get quite a lot of shapes out of this, but it's something quadratic in nature, something that feels like maybe something like a parabola, an ellipse, a paraboloid, an ellipsoid, a hyperboloid, something like that. But a second order function, it's going to have, a tangent plane feel, but that tangent plane is going to kind of curve a bit to try to wrap around the function, the surface of the original function a little better. Any questions on this? Again, I think the biggest thing here is being very, very careful at these points to plug in the value of the point that we're concerned with. That's what keeps this linear. Because otherwise, if I just put the partials in there as functions, clearly that's not going to be a linear function most of the time anyway. But evaluating those partials at the point of tangency and putting that in here, that's what gives the linearity, because I just have number times E minus E naught plus number times R minus R naught. That's where the linearity comes from. Okay, let me look ahead here. I'm going to skip over this bit. This is it's kind of a technical side note. I'm going to skip this. I'll publish this as part of the supplement tomorrow, but I'm going to knock out this bit on differentials. We might go a few minutes over. If you have to leave at 7:35, feel free to just pop out. But if we do go a few minutes over, I'll just keep that on the recording, and then you can come back and watch that last couple minutes at another time. So if you do need to pop out, no problem. You don't need to say bye or anything. Just leave the session and then just come back and watch the video later. But if you do have a couple minutes, we might go a couple minutes over. Okay, so differentials. Again, we know from Calc 1 the differentials are pretty closely linked to linear approximations. So we say for a function z equals f of xy, what we call the total differential, dz, is related to the differentials dx and dy. The differential is related to the inputs this way. dz equals partial f with respect to x at ab times dx plus partial f with respect to y at ab times dy. If we take dx equals x minus a, dy equals y minus b, we see that the linear approximation of x and y is just f of ab plus dz. So this is just an approximation to how the height changes whenever we get a change in the independent variables. So a change in x and a change in y combined together in this way to give me a change in z according to the tangent plane, which approximates the change in z according to the surface, the original function. Note that we can use a different notation for partial derivatives. dz equals partial of z with respect to x dx plus partial of z with respect to y dy. And this looks a heck of a lot like the chain rule written in a differential form. So we'll see this come up again in the next section. That's just kind of a side note there. This has a chain rule kind of feel to it. Okay, so let's look at example 5 then. I think this is a particularly interesting example. A lot of folks, say that they were never taught anything about finance or anything in school. Well, here we're looking at a monthly payment for a home loan. This is a function of the principal, the amount borrowed, the interest rate, the annual interest rate, and the number of payment periods. We'll call it that n, and that's usually the number of months. So we're going to think of the interest rate as being an annual interest rate and payments being per month. So the kind of monthly interest rate is I over 12. That doesn't really affect what we're going to do here, but just a side note on that if you're trying to work out some of these numbers on your own. If we take a principal of $100,000 at an interest rate of 6% annual interest rate, and a 240-month term, a 20-year loan, the monthly payment we get by plugging those numbers into a function we'll just call f. It turns out that that's $716.43. That's what your monthly payment would be for that home loan. Now, side note, that doesn't take into account property taxes, which can be significant. In some places, it's as much as the loan itself. Property taxes and, of course, insurance as well. So there are other considerations, but this would be just the cost that you would see for the loan. Also, for these values of the independent variables, p, I, and n, this function is fairly complicated. But it turns out that the partials are given here. The partial of f with respect to p evaluated at the point 100,000, 0.06, 240 is 0.0071. As a side note, note that this is a function of 3 variables. So we have 3 inputs. Our domain, our input space is the whole 3D space, and then our output space is another real line kind of off to the side. But none of that really affects what we're going to do here. We can't draw it very nicely, but we can do all of the same work that we had done before. But the partial f with respect to p at this point is 0.0071 approximately. Partial with respect to I is approximately 5,769. This number is multiplied by a very big number, which is why it's a small number. And this one is multiplied by a very small number, which is why it's a big number. And partial of f with respect to n, the number of payment periods, is negative 1.5467 or so. So these are our partial derivatives at this point. These are the slopes of those kind of tangent lines for those planes that are slicing through at this particular point. First, do the signs make sense? It's always a good thing to check. I've given you a lot of information here. Does this seem to be reasonable? If I increase the principal, if I borrow more money, having a positive number associated with that partial derivative means that I should pay more money per month. If I borrow more, I should pay more per month. That seems to check out. If my interest rate increases, if I have to pay more interest, my partial with respect to the interest rate is positive. If I have a higher interest rate, I should have to pay more money per month in order to pay off the loan in 240 months. That also makes sense. If I increase the number of months that I have to pay off the loan, if it's a longer term loan, if I have more payments to make, then my payment per month should be less, right? If it's a 30-year loan instead of a 20, I should pay less per month because I have a bunch more payments. So if I increase the term of the loan, if I increase N, my payment per month should go down. That makes sense. I have a negative sign on the partial with respect to N, with respect to the term. So yes, they do make sense. Let's use differentials to estimate the change in monthly payment per $1,000 increase in principal. So what are we looking at here? We're saying that df at PIN equals partial of f with respect to P of P naught, I naught, N naught times dP plus partial of f with respect to I evaluated at P naught, I naught, N naught times the differential of I times the change in the interest rate plus partial of f with respect to N, again evaluated at that point, times the differential of N, the change in N. So for part B here, a $1,000 increase in principal, dP equals $1,000, but DI and DN are zero. I'm not changing the interest rate or the term at all, just the principal. How does that change the monthly payment? And this should say, oh no, okay, that's good. So this is an approximate change in the monthly payment. DF is going to be, well, the partial with respect to P is 0.0071 times dP 1,000. And note that DI and DN are zero. So those other terms just zero out. Or this is $71 for each extra, sorry, not 71, $7.1. So for each extra $1,000 I borrow, I'll have to pay about $7.10 more per month. What if I want to estimate the change in monthly payment when the interest rate changes and the other things are held the same? To say the interest rate increases to 6.5 or 7%. Well, now dF is, well, dP is zero and dN is zero. So I'm going to have the partial with respect to I at this point is 5,769 times the change in the interest rate. I started at 6%, going to 6.5% is 0.5%. So 0.005. Or I calculated that was about $28.85. This is for 6.5%. And then for 7%, going up another 0.5%. So 6 to 6.5 added 28.85. 6.5 to 7 is going to add another 28.85 for 57.69. Because I'm on the tangent plane, everything is linear. So if I double the deviation, I double the differential. Everything works nice and linearly here in the tangent plane. And then what if I change the term? What if I went to a 360-month term instead of, so a 30-year instead of a 240-month? Well, now dp is 0. The principal is not changing. DI is 0. The interest rate isn't changing. What's changing is the term. DN, I'm adding 120 months, 240 to 360. So the change is going to look like minus 1.5467 times the change in the number of months, which is plus 120. And when I did that, I got minus $185.60. As kind of a side note, I can see that if principal increases by about 10K, that increases my monthly payment by about $70. If my interest rate increases by, say, 1 percentage point, that increases my monthly payment by, say, in the ballpark of $60, $70. If my term decreases, well, if it were to decrease by 120 months, that would increase my monthly payment by 185. If it decreases by a third of that, 40 months, that should increase my payment by about a third of $180 or about $60. So if N decreases by about 40 months, these all have in the ballpark of the same effect of increasing payment by something like $60 to $70 per month. Right, so 1 percentage point increase in interest rate is kind of equivalent to borrowing $10,000 more money, in a sense, or paying off your loan 40 months earlier. Right, so this kind of lever, so to speak, on the interest rate is quite strong. Okay, and we're almost done with this. 2 more small questions. We just made a few different estimates here, changing the principal by 1,000, the interest rate by 0.5 or 1 percentage point, the term by 120 months. These give approximations to how the monthly payment will change. Which one do we think will be the worst approximation and why? Well, a deviation of 1,000 units on a scale of 100,000, that's like a 1% deviation. That's probably not very far, so to speak, away from the point of tangency. It's only 1% distance away. That's probably not going to be too far that we're going to get a bad approximation. Moving 1 percentage point away or 0.5 percentage point away on a scale of 6% or so, I mean, 1 percentage point is about 16% change. 0.5 percentage point is about an 8% change. That's maybe a little bit bigger of a change, but probably not too far away. But going from 240 to 360 months, that's a 50% increase, a 50% change in my independent variable. I'm guessing that this one is going to be the worst. This approximation for the change in my payment going down $185 is probably not going to be super close. The other ones I would expect to be much closer to accurate. Just because, again, the relative change is so large for the number of payments going from 240 to 360 relative to the other two. All right, and then so we'll do part F, and then I have a quick Excel example too, just to kind of show you where these numbers come from in case you're interested. So part F, use differentials to estimate the change in the number of payment periods needed to maintain the same monthly payment if the principal increases to 110,000 from 100,000 and the interest rate increases from 6% to 6.3%. So again, I have df equals, I'm just going to say fp dp plus fi di plus fn dn. A much nicer way to write it, but again, we have to be very careful to remember that fp, fi, and fn are numbers. Those are the partials evaluated at 100,000, 6%, 240. And I want to set this equal to 0. I want the change in the monthly payment to be 0. I know that FP is, where was it up there? 0.0071. The change in the principal, we went from 100 to 110,000, so the change was 10,000 plus DFDI at the point is 5769 times the change in the interest rate is, we have to be careful here, it's 0.3%, so that's 0.003 plus FN, well, this is going to be actually minus 1.5467, just this number up here, times dn equals 0. So how does the number of payment periods have to change if my principal increases a bit, my interest rate increases a bit, to keep my monthly payment the same? How much longer will I have to pay on the loan, approximately? I get dn equals, that's not a subscript n, that's just dn, equals 0.0071 times 10,000 plus 5769 times 0.003 over 1.5467, and that's approximately 57. So this change, increasing the principal by 10,000, increasing the interest rate by 0.3 percentage points, would add about 57 months to my loan, going from 240 to 297 months, in order to maintain that same monthly payment approximately of around 716.43. Okay, and then the last thing I want to discuss, again, this is kind of a side note, so if you need to go, feel free to head out, but just so you know where these numbers come from, let me switch my screen share here. So I just threw together this Excel notebook really quick. If you're not familiar with Excel, that's fine. I'll kind of explain what I'm doing here. So here's P, I, and N. Our initial principal was 100,000, interest rate of 6%, N of 240 months. And then I'm interested in estimating the partial derivative for each of these P, I, and N. So I know that f of P, I, N is 716.43. Where did that come from? Well, that actually, so the number that I gave was actually the right number. That I pulled this out of a book, but I checked all the numbers first. So the payment you can get using this Excel function minus payment of the interest rate over 12, so 0.06 over 12, to change it from an annual to a monthly interest rate, number of periods of 240 months, and the so-called present value, the value of the loan today, the amount of money they're going to give you today in the present is 100,000. So that gives me a payment of $716.43. DF is the change in the payment. It's the updated payment for different choices of PI and N minus $716.43. So right now we haven't changed PI or N at all. So our change in the payment, of course, is 0. Let's estimate partial of F with respect to P. Well, to do that, I need to figure out what is F of P plus dP, comma I, comma N. I'm going to have to choose some delta. I'm going to have to choose some amount to change the principal by. I want it to be a small amount. I could pick 1,000 or maybe 100 or something like that. For reasons I won't get into, I don't want to pick it too small. But this should be small enough, but not too small to where things are going to start having problems on the other end. So what is my partial derivative with respect to P? It's F of P plus delta P minus F of P over delta P, approximately. Or it is F of P plus delta P, the blue number here, minus F of P, the red number, over delta P, this 100 here, the purple number. This new payment I just calculated the same way, but I just added that delta P or that 100 to the principal. And I see the partial is 0.00716, or we use 0.071. So that is where that dF dP number came from. If I wiggle I, the interest rate, a little bit, again, if I'm looking at F of P I plus DIN minus F of PIN over DI. So if I change the interest rate by 0.1%, going from say 6% to 6.1%, recalculate the payment using the payment function in Excel, being careful to divide the whole thing by 12, the whole 6.1% by 12. This gives me a new payment. I take the difference, divide by 0.001, and that gives me that $57.81. It's not exactly the number that we had over here, that was $57.69, but again, we're approximating the values here by taking basically a secant line approximation instead of a tangent line. And then for N, if I add one payment period, how does that change the payment? Drops it from $716.43 down to $714.89. And that's a change of minus $1.54. So that's where that negative 1.54 roughly comes from. So now let's look at for payment of a principal of 110,000. I just realized I switched screens a couple of times here to point to things, and I only have you on Excel, and you didn't see the OneNote, but I think you can follow along. But if the principal increases to 110,000, if the interest rate increases to 6.3%, our claim was that for DF to be 0, we needed to add 57 months, or we needed to have 297 months. And we see that, I mean, we increased our payment by $15. It didn't stay exactly at 0. But remember, this is a linear approximation. Changing N by 40 and increasing the principal by 10,000 is a pretty decent deviation. And we did pretty good to stay within, say, $15 of our original monthly payment. And we had to do a lot less work than we would have to do with evaluating this function and doing a whole bunch of trial and error. So what about parts, B, C, and D? If our monthly payment increased up to, if our principal increased by 1,000 up to 101,000, if our interest rate was 0.06, and our payment period was 240, what was our increase in monthly payment? We estimated it to be $7.10, and it's actually about $7.17, pretty close. off by 7 cents on a scale of $7, off by only about 1%. If our interest rate increased to 6.5 or 7%, where this is back at 100,000, for 6.5%, we'd see an actual increase in monthly payment of about $29.14. We estimated $28.85. So we're only about 30 cents or so off on a scale of $30, again, within maybe 1% error. If our interest rate increased to 7%, our actual payment would increase by $58.87 per month, and we estimated about $57.70. So we're off by about $1 on a scale of about $60, a little more than 1% error, because we're getting further and further away from that point of tangency. And then lastly, increasing the number of payments to 360, we'd see an actual decrease in monthly payment of about $116, but we estimated a $185 decrease. Again, because that 360 is so far away from 240, it's like 50% more. Our approximation no longer is a very good approximation. $180 estimate versus $116 actual difference is probably not enough for us to be happy with that estimate. This is pushing things a little bit too far. Okay, so that finishes up for today. Again, the only thing that we really need to wrap up is this little section on differentiability. It's a little bit more of a technical note, so that'll probably be a short 15-minute or so video that I'll post. I might even just try to knock it out tonight. And that'll be the only remaining supplement for this week. That wraps up 14.1 through 14.4 for this week. Next week, we start into 14.5 through 14.8, continuing on in chapter 14. So thanks for bearing with me for these extra few minutes. And again, if you had to go, no problem. You can just watch the recording later on.